I kind of like the problem in the sense that it makes someone think, right? Or is that I'm not sure. In a sense. So this is problem, homework problem, Gordon. Yeah. Did you do that? No, you're not listening. First one, I guess, right? Yeah. So, how did it go?
We're talking about all the charges in the square. Like there's two electric, there are two negative and two positive charges for each other.
Okay.
How was it when you were connecting from there? There was a significant difference, or?
Yeah, I didn't like it as well, obviously, but it seemed like when you're on the left side of this board, it might be like a fisheye lens, and it was just kind of hard to see. Like if I wasn't listening while you were saying that, I probably would have had a couple times writing it down. Yeah.
Do you think it might be good to do it two of them?
Maybe.
Like, because I sometimes think that the bird's eye view is also good. I point here and there, so that also helps.
Which that's good that you can see the whole board.
Yeah, exactly.
It's just one of the things.
It's always there. Yeah, I heard it. So let's see. Hello, Matt.
Hello.
Oh, thanks.
You're fine. We're good.
I was asking Christian how it is to read because he was on the other side. He was online last time. So do you have anything specific after so many weeks that I should change or anything?
I mean, as far as like the reading of the whiteboard goes, you think you do a pretty good job of like saying what you're writing down. So if I can't exactly read it, I can hear what you're writing, or you will say it. So either I can go back and watch the lecture, or if I'm paying attention, I can, if there's any questions, I can kind of just.
So it's not perfect, but manageable, right?
Yeah, it's manageable.
Curtis, did you get the question? Is there anything you would like me to do to change the zoom in or anything?
Nothing in particular. It's been pretty good so far.
Okay, good. Okay. So I posted homework 7 just about, I think, half an hour back or so, or maybe an hour back. And this is due Wednesday. Earlier I said it might be due Monday. And homework 8 is not posted yet, but it will be due on October 7th. And midterm 2 is the Friday following that. Okay. We introduced the idea of a dipole last time, and I want to generalize on that concept. So what is a dipole? Maybe I can begin by asking that.
Two charges of equal magnitude and opposite sign separated by some distance.
Separated by a distance. But what if we have two charges that are not of the same sign, or equal and opposite charges, right? That's what we say for dipole, which is correct. But Is it possible to define a dipole for such a configuration? Probably not, right? When we think of it as a dipole as equal and opposite, it is not. It is also true. I'll sort of emphasize why that is necessary. But we are going to generalize the definition of a dipole, which will allow us to do such a thing. And we will see how things proceed. So let's define what is called a multipole expansion. In fact, the idea is, so if you have a single charge, it will be called a monopole. And then you'll have a dipole. What's the next? Tripole, but it's quadrupole. Have you heard of a quadrupole? A charge, quadrupole charge?
Yeah.
Yeah. So, spelling?
RO.
RO?
I would think quadruple
I think.
or quadruple. The U.
Doesn't seem correct. Okay, I'll let you guys check it. So the next is, I think, octuple.
So it's kind
Yeah, why not? Extra credit. Extra credit for, whenever I cannot answer something. Yeah, extra credit to not just a spelling, just do something about quadruple. That's an interesting thing that comes up in this is that, am I in a position to tell that? Okay. Yeah, let me say that, something related. Basically, the statement is that gravitational waves require the mass distribution to have a quadrupole moment, but probably that is not completely transparent unless I define what a quadrupole moment is. So let's wait for a moment. So quadrupole and so on. Okay. So that's the idea. So a single charge, of course, will be a monopole, an electric monopole for that matter. But let's see what we are trying to do. Remember that electric potential. This is sort of the building block for the whole of electromagnetism, electric potential for a point charge or a point charge is also 1 over r minus r prime. Actually, 1 over 4 pi epsilon. Get that. And there's a q, right? If you have a charge point charge q. If I set q equal to 1, epsilon naught equal to 1, then this is called the Green's function. This way, it just seems like I'm giving it a name, but when you do a differential equation, that's a solution to the inhomogeneous differential, a particular solution to the inhomogeneous differential equation. So that's what it is. So let's look at this more closely, and let's do some manipulations for that to get what we want. So let's take a simpler example. Let us say, yeah, let's do Taylor expansion. Taylor expansion. What do we understand by Taylor expansion? So how do you guys know Taylor expansion is? What comes to your mind when I say Taylor expansion of a function, let's say at a certain point?
Like if a function of you expand it into like so you have x and a quadratic term and like x squared x cubed, you have the.
So if I'm not wrong, this is f of x would be equal to
1 plus
f of 0 probably. F of 0 plus f of 1, no, f of 0 itself, but now we will say x over 1 factorial and derivative of f evaluated at x equal to 0, correct? And then it is x squared over 2 factorial. And second derivative of f with respect to x squared, and so on. Great. This should be thought of as x plus 0. So if I had a small variable in there, so let's say f of x plus 0, so let me do f of x plus another point x prime. So I replace all these zeros with x prime. So f of x prime plus x over 1 factorial f over x at x equal to 0 plus x squared over 2 factorial second derivative of f with respect to x squared, oh, not x equal to 0 now, right? X equal to x prime. Just copying there. So x equal to x prime there, and so on. That should be, is that correct?
Does the x not change too in the numerator?
This one?
Does that not change like x minus x prime?
This is, oh, yeah, x minus, yeah,
I'm
that's
trying to
correct.
remember the difference.
Yeah, that's correct, that's correct. That's, correct? Yeah. Second, yeah, that's correct, right?
I think so, because technically the numerators are x minus 0 in the first one, and then that's the difference between like a Taylor and a Maclaurin series expansion, right? Is that one of them assumes that it's set at the origin at 0, and then they redefine it for if it's moved like this place at all.
Yeah.
So I think that the numerators, I think it's x minus x prime to shift it back, but I don't know for sure.
No. So, yeah, but I do know what he's suggesting. Okay, let's see. Okay, how do you do this? I'm stuck here. Okay. So, I'm saying it's not. And why am I saying that? Yeah, so what you typically do is you have f of x delta. Yeah, I think the way you're suggesting is you would do f of x if you want to expand about x prime. Okay, so okay, then you would say this is f of x prime, right? Plus x minus x prime of derivative of x minus x prime, and this is a x equal to x prime, and this is 1 factorial, plus x minus x prime squared over 2 factorial. You almost made me believe that, yeah, that was wrong, yeah. So this is, I think this is what it is, yeah. Right, that's how it is defined. But then I want to rewrite this in that form. So why I say that? Okay. Let me, instead of x, I put an x plus x prime, correct? So wherever I see x, I have to put an x plus x prime. So then it is, so what happens to this then? This doesn't matter because it is even at help you?
I see what you're doing, but now it does seem like the first term is.
Huh? Am I doing this correct?
You're saying that the first term should be.
Yeah, first term there is a problem then, right? So x is equal to, if x is equal to 0, that's f of x prime, that's correct. Seems like.
Oh,
Here.
it is because it's an x prime. You don't have to replace it. And the one that you're pointing at, it's already x prime.
Yeah, yeah, so I don't have to replace it, right? So this is x prime, so I don't, so x so here, from here to here, I'm going to replace x to x plus x prime, and to keep x prime stay the same. Okay, I think that's what, so x goes to x plus x prime, f of x prime stays the same, and x minus x prime now is x. Okay, good. And yeah, this seems to be the same. So now x plus x prime, right? So x, the new x is your old x minus x prime. This is x equal to 0 now, right? What do you say here? No, this is x equal to x. Yeah, x equal to x prime, I suppose.
Oh.
Right? I think so. Because you want to make it at x prime. Geometrically, it makes sense to me, but I'm thinking of it algebraic moves, so it's confusing. Okay, better.
Algebraically, those should cancel also, right? You should
That's what I was thinking, but it has to be evaluated at x prime. So let's see. So you're concerned about x minus x equal to x prime, right? So earlier it was x equal to x prime, but then x got replaced to x plus x prime, and x prime got replaced to x prime itself. So you would say this is x equal to 0. No, because I'm evaluating at x prime, right? It's a derivative at x prime.
I see, but why wouldn't that change in the limit?
Yeah.
Or not in the limits, but I guess.
Yeah.
I mean, I can look into this stuff.
No. Might be important. Hold on. Matt and Curtis, any questions or suggestions?
Nothing yet.
Yeah. Any help? Okay. Okay, give me a second. Okay. So let me, because.
Well,
Let me try the following, okay? I'm going to put it, how about this? Because this is not the expression I want to, so I'm not very confident about this, but suppose what I was going to do is that I'm going to flip x and x prime, okay? Because symmetric, who cares what is what? So this is f of x plus x prime over 1 factorial plus derivative of with respect to x. Then since it is evaluated at x, I don't have to do anything. No x equal x prime and all that. And this is x prime square over 2 factorial times second derivative of f with respect to x squared. That's it. Now, does that make sense? Let's see. So now if I were to compare this with this, so now let's see how I want to proceed. So I want to get this expression from here. So I would say x going to x plus x prime. And x, sorry, no, that's not enough, right? X minus x prime going to x prime, right? So that's what I want to get. And wherever there is x prime, I want to say that's x. That's what I want. Right? And let's see if I get this then. So I start from here, right? So x is x is how about this y prime? So this is now I'm substituting, right? So this is equal to x prime is equal to x, which is y. So now we can solve for this. So x is equal to y prime plus x prime, which is y prime plus y. And x prime is equal to y. Okay. So x is y prime plus y. Okay, now we are thinking. F of x prime is y plus x minus x prime is so x minus x prime. X minus x prime is y prime. And df by dx now evaluated at x equal to x prime, which is x equal to y. Yeah, now it works, right? By prime squared over 2 factorial. X equal to y. And so then I replace y with x. And so now this is correct. Yeah. Struggled a little, but I think this is okay. And any questions there? Hopefully that didn't bother too much. Gordon? It seems to.
I'm just trying to.
Okay. The idea is that, see, remember, we want to think of primed as sources and x as observation points, so that's fine. So I want to separate out the sources. Dipoles, monopoles, quadrupoles, they will all be sources associated with the configuration. Just for a small realization as to what could be going on here. So there's a nice feature in here, which is we won't use this actually today, but it has an implication when you do something called spherical harmonics, which probably we won't touch in here. All this f is on the right, so I can write this as 1 plus x prime over 1 factorial derivative with respect to x plus x prime square over 2 factorial derivative with respect to x square, and so on. And this is f of x. That's a reasonable thing to do. And this is the same as writing 1 plus x prime d by dx over 1 factorial plus x prime d by dx squared over 2 factorial. Notice when I square this, this looks like, so x prime d by dx squared is actually x prime d by dx twice, right? And one might be bothered, oh, what about the derivative acting on this? But these are independent, so x prime can come out of this. So only then that's allowed, right? So that's x prime square, second derivative square. And so on. And does this series ring a bell? That's an exponential of x, right? Very good. So that means that Currently, this is equal to if the derivative on an exponential in the abstract sense. So what does this mean? So if I were to give you this to begin with, what does an derivative on the top of an exponential mean? It means this. This is a compact form of writing. Like always a function has a series representation whenever like x. What do you mean by exponential of a matrix? Like, so always expand that out, and that's what it means. And that's equal to f of x. So often in another context, again, we won't be using this at all. This is called a translation, right? What is happening is that f of x becomes f of x plus x prime, which is a translation. You move the origin a little bit. So this is called a translation operator in that sense. So whatever is sitting on the exponential is called an operator for that symmetry or the transformation. And that has implications when you do group theory and so on. But we won't explore that too much here. Okay, so we want to capture this series expansion here. And let's, so we have something like 1 over r minus r prime that I want to explore. So let's think of 1 over magnitude of one dimension for it. We'll come to 3 dimensions very quickly. Let's say this is x minus x prime. So that's all I want to look at. And then it seems like you can do the same idea there, right? So you would do, so think of this as an expansion. So it is 1 plus, it's not plus, now it is minus, right? So it is 1 plus minus x prime if you want, over 1 factorial times derivative d by dx plus minus x prime squared over 2 factorial second derivative squared and so on. And then f of x, which is basically x prime setting to 0, that's 1 over magnitude of x. Start x itself, remember x is the absolute value of the quantity, right? So x could be positive and negative. And it's not at a vector. Later on we'll come back, but not later on, within a few minutes we'll do this for a vector scenario. Okay. So this is equal to, if you want, this is equal to 1 minus, right? There's a 1 factorial and help here. What is derivative of magnitude of x squared? Yeah, since it is a toy model anyway, yeah, let me do the following. I'm going to be doing this. This is just a warm-up for this. So let me just say that x and x prime is greater than 0. It's just a warm-up problem. Let me not get into the slight forking there of what happens when x is greater than 0 and what happens when x is less than 0. Then I don't have to put this magnitude sign. And then these derivatives are significantly simpler. Okay. So both are greater than 0, but we don't know which one is bigger. Right? X could be greater than x prime, and or x prime could be greater than x. So this is x prime then, and derivative of 1 over x is 1 over x squared, correct? And there is a negative sign, so that goes away, and that's x squared. Next one is plus again, right? X prime squared, 1 over 2 factorial, and derivative of that x. So 2 derivatives will make it what is it? X cubed, and I'm missing something? Negative because second derivative, right? So first derivative brought in the negative, second derivative killed the negative. But still I'm missing something. What am I missing? That's a silly small thing. Important, I guess. Let's do second derivative of x. So what is second derivative of x? Oh, 1 over x. So that's the first derivative of minus 1 over x squared, right? And when I do the second derivative, minus 2, right? So that's x cubed. There's this 2 there, right? So it's clearly seen that d raised to n by d raised to x raised to n of 1 over x will be equal to n factorial by minus 1 raised to n divided by x raised to n. Right? So this is actually having a 2 factorial on top, but then that cancels out. So I don't know why. Correct. And sign was not a problem because this always comes, this also has a sign there, right? Minus 1 raised to n x prime square, correct? And that's equal to plus x prime cube over x raised to 4, and the pattern is clear. And I was doing magnitude of x. Let's see if this is fine.
So
Yes.
there's no like 1 over 2 prime over 2 prime.
1 over, is that, am I missing something? Ask me again, sorry.
So like it's 1 plus 1 over 1 prime, and after that.
Yeah, there is nothing, this is not there.
Okay.
Yeah, I was thinking that 2 prime coming in, then I realized that. Correct? I think that's correct. Okay. I think so. I can check actually on this. No, I don't have it. Here there's 5 more. There is a small issue here that if x prime was greater than x, then this keeps growing, right? This number keeps growing. So it's convergent. So let's just also put the condition that x prime is less than x. But if x prime was greater than x, I could have restarted the whole thing. Who says whether this x or x prime? I would have put a minus sign in front and expanded about so there's a symmetry. So I could have got that also. Okay. But this is the same as. Oh, there is a one more term, something missing here, dimensionally. I made an error. Dimensionally something is wrong, right? The dimension of this is 1 over length. So what's wrong? Because we missed that, right?
Oh.
Error? Yeah, my bad. Okay, so this is equal to 1 plus x times summation of, usually you say n, but in this case we will use L. There's a meaning for that. This is a standard thing. L equal to 0 to infinity of x prime over x raised to L. I think so. Oh. Seems correct, right? What can be? Okay, so and this is x prime less than x, and if x prime was the opposite, then you just it's x on the top. That's what happens. Okay. Just for telling you something related, where else do you? I mean, this is meaningless in the sense I could have used anything, right? L has no meaning here. L is just a label I used to. But typically, where do you use small l? This is pretty standard, at least in the modern literature. In quantum mechanics. Yeah, angular momentum, right? And that is exactly what it is. It is like this will all get connected, hopefully, later on. Like, so this L is going to be related to the angular momentum hydrogen atom. There is an L quantum number. That's pretty much this L, but at this point, this just seems like just showed up, right? So that's why I used L. Okay, so now we want to do exactly the same thing for a bigger problem, and that's a three-dimensional thing. So what do we mean by Taylor expansion? So let's go back to the Taylor expansion we knew, right? So what if you have f of x, y? How do you do Taylor expansion? Correct. So here we did x. Now we have an x and a y. This is not second variable here. This is x comma y. So I can expand about x and I can expand about y. First, let's expand about x. So this will be 0. That's the same as what I did there. But now there is a y there, right? Plus x over 1 factorial and derivative of f with respect to x. And this time, this is x comma y. And this is at x equal to 0. And let me not write the second one, right? You can keep going just to save me some effort. Let me keep going. But that's good. But now I can expand each of this. So this is a function of y. This is also a function of y. I can expand those things in y. So I will write. So this is f of 0y plus. This is just the first one again. F of 0, 0, 0, 0 plus y over 1 factorial plus derivative of now y. Sorry, y with respect to f of xy. This time expanded about x equal to 0 and y equal to 0. This is the expansion of this quantity alone. I can expand the second one also, plus, and this keeps going, plus x over 1 factorial, derivative of f with respect to x, of x comma y, x equal to 0, and you do the y equal to 0 also, plus the next term, which is x over 1 factorial, and there is a y over 1 factorial, and this will be second derivative, right? So d by dx and d by dy. And this one has become a column now. Similarly, you have to keep going on both sides. Right? Is that clear what I mean? So expansion in an expansion. Right? If this was 3 variables, this will become expansion and third variable. But what is the generalization here? Notice that x and a y here, right? Now, if I were to rewrite this, so let me go to the other board. If I were to rewrite this, f of xy is equal to f of 0, 0 plus That is an 1 over 1 factorial. Collect all the terms as 1 over 1 factorial. That is, this is brackets. That is x times d by dx of f plus y times df by dy. And I should actually write this is now x equal to 0, y equal to 0. This is x equal to 0, y equal to 0. And so on. X times d by dx plus y times d by dy. What is that like? That's a vectors.
R times.
This will be r times the gradient. Very good. Right. That way we can take it to the next dimension, right? This is 2 dimensions and 3 dimensions also this works. Right, but that is to be taken at x equal to 0. So this is the same as f of 0 vector plus 1 over 1 factorial of r dotted with gradient of f evaluated at r equal to 0. The vector if you want. And so on. Right, the next one, just so that there is no non-triviality, there's no ambiguity there. So this is R, but the next one is squared. All right, so this is so this is to be, yeah, this is a little tricky. Let me use Ri, right, and Rj, and this is del of I. L of J. Is that making sense what I mean? What that means is that this R is dotted with this, and this R is dotted with this. There are dot products, 2 dot products. Is that clear? But when we write it in this form, that will be a simplification. In our example, we are not interested in this. We want to symmetrize with respect to source and observer. So this becomes f of r. Right. That's what we have, x, right, plus 1 over 1 factorial of r prime dotted with gradient of f of r. Since I'm going to evaluate it at r, I don't have to actually write this explicitly. Right? So that was the feature here, that I didn't have to write this explicitly. There was a small simplicity there. So now I don't have to write that. So then I don't have to get rid of this. So then what happens is that this is plus 1 over 2 factorial. Now instead of doing this, I can actually do r prime dotted with gradient square. Like there I couldn't have done this because I had to set r equal to 0. So that was a small caveat. Just a convenience, otherwise it's the same thing. And this is true for 3 dimensions too. That's your Taylor expansion in 3 dimensions using vector calculus. Okay, any questions? Anything that bothers? Okay, the last 7 minutes. So that's what this is. So that's your Taylor expansion. And now let's do this for 1 over r minus r prime. So this becomes, I have a set r prime to 0, so that's 1 over magnitude of r. So this time I want to keep magnitude of r because we're working with the electric potential, which is the magnitude of r, plus 1 over 1 factorial plus r prime dotted with gradient of, this is again 1 over r, right? 1 over, let me just say r now, right? This is simple r, right? The magnitude of r is just r without a vector sign, and we know how to operate that. Now let me write one more term. And probably, as you can probably see where I'm heading for each, so one will have a monopole, one will have a dipole, the next one will be quadrupole, and so on. That's probably going to capture, but probably not right away today. But so this is 1 over r again, and so on. Gradient of 1 over r is equal to 5 minutes. I'm wondering how far I'll reach. What is gradient of 1 over r? Minus 1 over r square and r hat, right? So minus 1 over r square, you take the differentiation, and then you do the gradient of r itself, magnitude. So this is r hat. The relation is gradient of r is r hat. So that's our identity, which will be running through the whole course actually. So that's very useful. R hat over r square. We'll write this as, because we want to operate it again, right? So it will be convenient to do this as r over r cubed. And we'll come to the next terms next time. So this is equal to 1 over r plus 1 factorial is 1. So it is minus of r prime dotted with r over r cubed. And so if I bring in all the charges and potential, 1 over 4 pi epsilon naught times q is equal to 1 over 4 pi epsilon naught q over r minus r prime. And the next one seems to be having a minus sign. Really? Minus sign? Where did that minus come? No, right? There was a minus sign here, so this is plus. This was a plus because this is a minus sign. Oh no, it is a minus. What? The minus sign?
Oh, no, your second term should have been minus because you have r minus r prime.
Oh yeah, this is not plus, so this is minus. Yeah, thank you. Thank you. So that is plus, this is minus. So this is plus. Yeah, perfect. Okay.
Like that, is it minus again?
This
After
is
plus and then minus.
This is minus, plus, and then this is minus. That's okay. Yeah, thank you. Yes, it alternates sign. But in this form, this is actually and this is equal to 1 plus 1 over 4 pi epsilon naught q times r prime dotted with r over r cubed. Now, does this ring a bell? This is familiar. Dipole, right? If you remember the expression for the dipole from last week or the last class, this seems to be a dipole. And that's your charge. This is a monopole, that's a dipole. Next one, whatever comes here will be a quadrupole and so on. Right? So we're going to define our dipole as, suppose you have Q1, Q2 at position R1, at position R2, then our dipole will be defined as Q1 times R1 plus Q2 times R2 plus Q3 times R3 and so on. So it doesn't matter whether it is Q1, how many charges are there, whether it is positive, negative, doesn't matter, that's okay. Now there is a similar thing that you see in forces, right? So if you were to think of these positions as forces, you can think, or let's say charges as forces, right? Think of total force. So this is an extra credit problem. The total force is F1 plus F2 plus so on. Right? And I can also define my torque total similarly as F1 crossed with, no, R1 crossed with F, right? F1. The moment of force plus R2 crossed with F2 and so on. Agree? Is this definition unique? And by that, what I mean is that, how do I define this? I'll ask this question more precisely. Yeah, the point is, torque depends on the definition of the origin, right? So torque requires, so how do you define your torque? Right? You have a coordinate system, there is a mass here, and a force acts F. And then you say that this is R, and torque for a force is R crossed with F. So it seems like if I move the origin, torque changes. Right? So the torque total will also change. Okay. So the question is, the extra credit question is, under what circumstances does this torque become unique? It is unambiguous. In general, the torque depends on the definition of the origin. Right? So actually you guys do this in engineering, right? If you think of your statics course, you will write an equation for the force, you will write the equation for the torque, and so on. And there is a theorem you use somewhere in between that says that under these circumstances, this is actually an independent equation. Otherwise, it is ambiguous. So the point is, when does this become unambiguous? There is no dependence on the origin. Something happens to this becomes unique. That's kind of maybe it's a little vague question, but explore it. I want you guys to think about the force, moment of a force, right? You can second extra credit. What is this? This is the first moment of a force, right? What is the second moment of a force? Explore, just look it up. Actually, I don't know the answer. I'm not answering your question because of it. Okay, and I'll stop here. I already went. Thank you.
What's the second?
So the first question is, it's a little vague. This definition of the torque depends on the definition of the origin.
Mm-hmm.
Under what circumstances does this become independent of the origin? That's the first question. And the second question is, torque is defined as the first moment of the force. That's the way we would say, or cross that, right? So is there anything called the second moment of a force? And I don't know the sense of